Welcome to the Probability and Statistics course. In our last lesson, we talked about discrete probability distributions, and this time we are going to see about continuous, when we have continuous random variables. We have seen the binomial and the Poisson distribution, and this time we are going to see two continuous distributions. So we are going to see the normal distribution and the exponential distribution. The normal or Gaussian distribution was introduced by Abraham de Moivre in 1733, and first it was used to approximate the binomial distribution when n is large. Now, in practice, the importance of the normal distribution is that many random phenomena can be approximated by it. We have actually the central limit theorem, and we are going to see that in many cases the normal distribution is used in order to calculate probabilities. Now, the normal distribution is one of the most important distributions, so we are going to spend some time to understand exactly how we should calculate probabilities using normal distribution. We have to make sure that we know the normal distribution and how to calculate the probabilities. Let's see what the normal distribution is. It is denoted by the capital letter N, and the parameters, as before, this is a family of distributions, and the parameters of this is its mean and its variance. So the normal distribution is given here for x could go from minus infinity to infinity. The normal distribution, as we said before, we are talking about continuous random variables, so x can take any number between minus infinity to infinity. Our random variable can take any number between minus infinity and infinity. Now, the expectation, the mean of the normal distribution is mu, its first parameter. The variance is sigma squared, its second parameter, which we would need in here in order to specify the normal distribution we need. And also the normal distribution, it has the property, it's bell-shaped, it has the shape of a bell, and it is symmetric. It has this important property here. Now, a special normal distribution is the standard one. The standard normal distribution is the one that has the normal distribution that has expected value 0 and variance 1. So if we replace the mu equals 0 and sigma square 1 in our original formula of the normal distribution, we can find the formula for the standard normal distribution. Here we are going to see why the standard normal distribution it's so useful. We see that when the random variable x follows a normal distribution with mean mu and variance sigma square, then by doing this transformation here, by taking out of the random variable the expectation and divided by the standard deviation, this will be a new random variable which will follow a normal distribution again, but with mean 0 and variance 1. And so it will follow a standard normal distribution. Here we have a plot of our standard normal distribution. We see that it is bell-shaped, as we said before, and it is symmetric. It is symmetric around the mean. We are talking about the standard normal distribution here, so the mean is 0. Now, for the standard normal distribution, we also know that 68.26% of the area is between -1 and 1 of the area underneath the curve. This area is 68.26% of all the area here underneath the standard normal distribution. Also, we know that 95.44% of the area is underneath the curve between -2 and 2. So this area here is 95.44%. And also 99.74% of the area underneath the curve is between -3 and 3. We are going to work through an example to see how we can calculate probabilities. So we have that the temperature during a summer month is normally distributed with mean 25 and standard deviation 3. We see here, again, we remind that the standard deviation has the same units as our original random variable, and that's why it's more preferable to use than the variance, which will be squared. So for this example, we have that we want to calculate the probability that the temperature is between 25 degrees Celsius and 30 degrees Celsius. Also, we want to find what is the probability that the temperature will exceed 23 degrees Celsius. We start by asking the first question, what is the probability that the temperature is between 22 and 30? And we actually ask the question, what is the probability of our random variable x to be between 22 and 24? So by denoting with x our random variable to be the temperature, we want to find this probability using the normal distribution. What we can do is that it is very difficult to work with the normal distribution and calculate it for the x. We want to find the area underneath the curve. So what we usually do is that we transform our random variable x to a z, and then we can use tables which are ready and gives us the areas underneath the curve, the areas that we are interested in. Now, every book in statistics has tables which have calculated the areas underneath the standard normal distribution. We just need to be careful when we read the numbers on the tables, which area exactly do they have calculated. So, if, for example, a book has the normal distribution and gives us this area, it actually gives us the probability of z less or equal to a number. If, on the other hand, it gives us this area, it gives us the probability of z greater or equal to z. Usually, books will have a plot of the standard normal distribution they use, and so we can make sure that we read the right values from the tables. We go back to our example. As we said before, our standard technique is that we need to transform our original random variable to a standard normal variable. So what we do is that we take out the mean and we divide by the standard deviation, as we said before. The same way, of course, here we take out the mean and divide by the standard deviation, and this side. So what we have to calculate, we have translated our problem. We have this problem now to calculate the probability that the random variable z now, which follows a standard normal distribution with mean 0 and standard deviation or variance 1, is between -1 and 2. Now, as we said before, the values of usually the cumulative distribution function of the standard normal distribution is given in tables. Most tables prefer to give these probabilities for z greater or equal to 0. We are going to see later on how we can obtain values, how we can calculate values for z less or equal to 0. Now, as we said before, this is not a rule. Books may not give these probabilities only. They could give from the other side of the distribution. So you have to be very careful. Now, here we have the standard normal distribution, a graph. We always need to have a graph to see which probabilities exactly do we want to calculate. And for our example, we're actually looking for z to be between -1 and 2. So we are looking for the area underneath less than 2 and greater than -1. So in fact, we are looking for this part here, this area here. So we can say that this is actually the same like saying that we are looking for the probability of z less or equal to 2, as we showed before, minus we have to take out this area here, because we only want the remaining area which is shown in here. So this probability, it actually is the green lines, and taken out this area here, which is the probability of z less or equal to -1, we are here the area that we want to calculate. So we see how important it is that we have a graph in front of us when we calculate probabilities. Otherwise, it's very difficult to understand how we can make our problem simpler. So, as we see here, this is the cumulative distribution function up to 2, so it's phi of 2 minus phi of minus 1. So now from the tables of the standard normal distribution, we can find the value of the cumulative distribution at point 2, which is 0.9772, and then we need to calculate the second probability, the probability that z is less or equal to minus 1. Now, usually this won't be given in the tables, in the standard tables of the standard normal distribution. We said the tables show for negative numbers of z. So in order to calculate this probability here, we need to note that the area of this probability, the area under the curve, is actually what we want to calculate is this area here. We want z to be less or equal to minus 1. Now, we know from the properties of the normal distribution, and we can see in the picture that it is a symmetric distribution. So if we go on the other side and go exactly at the positive number of what we want to calculate, we can find a symmetric area. So we can actually go at point 1, and what we want to calculate is this. This area under the curve is exactly the same as this. So this will be equal to the probability of z greater than 1. This is a continuous random variable, so the equal sign won't make a difference. In order to calculate now the probability that z is greater than 1, we change it. As we said, most tables gives probability of z less or equal than a number and not greater or equal than a number, most tables. So if we have a table like this, we change the probability of z greater than 1 to 1 minus probability of z less or equal to 1. The area under the curve, all the area under the curve, should be 1. And so, going back to our example now, we have that 1 minus the cumulative distribution function at point 1 is equal to 0.1587. And to answer the question of what is the probability of z being between minus 1 and 2, we take the two probabilities we have calculated and we find that the probability that z is between minus 1 and 2 is 0.8185. Now we are going to try to answer another question on probabilities for the same example. To calculate another probability, again the same way, when we have the normal distribution, we would need to have a graph in front of us so that we know exactly which probabilities we are looking for, and also we would need to to consult a table to find the probabilities that we'll need to calculate what we want. So the next probability we are looking is what is the probability that the temperature will exceed 23 degrees Celsius. So we're looking for the probability that x is greater than 23. Now for this case, again, as we said, always we start by transforming a random variable to a random variable which is which will follow a standard normal distribution, and so we take out the mean and divide by the standard deviation. The same way this side. So we have that this is z, this is the random variable z. We are looking for the probability of z greater than minus a third. Looking at our graph, what we actually want to calculate, the probability that z greater than minus a third, is we are looking for this area here. We are looking at the probability that z will be in this area, and we have that, as we said before, that most tables do not give probabilities of z greater than something, and especially here we have a negative number. So we know that from the symmetry of the normal distribution, it's the same with calculating the probability that z is less than 1/3. So it's the same as finding the area here. Looking at tables, we can find the number that corresponds to the cumulative distribution function at point a third, and we have that the probability of z greater than minus a third is 0.6293. Now, using the normal distribution, we can do the opposite thing we did here. Instead of calculating the probability, instead of calculating the area under the curve that corresponds to a point, we may want to ask which point corresponds to some area we want to have. So this, for this example, is a question like here. We would ask what is the value which will be exceeded by 10% of the data. Because we want to be exceeded, we are looking at the upper tail area of 10%. Now here, the value which we are looking is actually the point of the normal distribution that will correspond to an area of 10% on the upper tail. We look here again on our standard normal distribution. We have that we want the probability of x, the point that the probability of x less than x will be 0.9, because we wanted 10% to be exceeded, so 90% should be less than that point. So we are looking for 10% to to be exceeded, which is the same as 90% not to be exceeded in the area under the graph. And again, the same way, we would need to transform the random variable to a standard normal variable. So we take out the mean, divide by the standard deviation, and we have that this probability should be equal to 0.9. Now, this is actually the cumulative distribution function at this point here, x minus 25 over 3. So we are looking at tables, we can find this value. We have that. The value that corresponds, that is 0.9, is actually at 0.28. So for the cumulative distribution function to be 0.9, we have to have that z should be 1.28, which z is x minus 25 divided by 3. It should be equal to 1.28. From here, doing the calculations, we can see that the point on of our random variable which corresponds to the probability we wanted to calculate is the point 28,84. Now we have worked probabilities using the normal distribution. As we said, is a very important distribution. Now we are going to see another continuous. We are going to see the exponential distribution, which is associated with the Poisson distribution, the one we saw in our last lesson for discrete random variables. So the exponential distribution, denoted by the capital letter E. Again, we have a rate lambda here, like for the Poisson distribution. We said that these two distributions are associated. And the exponential distribution can be used when we want to measure the time between successive events that occur with rate lambda. Now the Poisson distribution, we're measuring the number of outcomes when we have an experiment. Here we're measuring the time in between these outcomes, these events, these successive events. The exponential distribution here, given for x greater than 0, for x less or equal to 0, and the cumulative distribution can easily be computed from the probability density function is given here. The expectation and the variance for the exponential distribution is given here. The mean is 1 over lambda, and the variance is 1 over lambda squared. We remember here that for the Poisson distribution, the mean was lambda. So we note the difference from the Poisson distribution, the exponential distribution. We have to be careful not to confuse them. So let's see an example. We have breakdowns in a system that occur with an average of 24 per year. Now, if we can assume that these breakdowns follow a Poisson distribution with this rate, 24 per year. And the Poisson distribution, we see how it is associated with the exponential. The time between the two successive breakdowns will follow an exponential distribution. We see that the time is a continuous random variable, the breakdowns are discrete. So we want to calculate what is the probability that we have no breakdowns for a period of 2 weeks. So we actually ask, what is the probability that our random variable here, x, will be greater than 2 weeks? The random variable will be the time between two successive breakdowns, whereas the random variable for the successive breakdowns is a Poisson. Here x is an exponential, the time is an exponential. For the exponential distribution, lambda is 24 per year, and so we have that, because our question involves weeks, we measure in weeks, we have to calculate lambda in weeks. We have to always be very careful with the exponential and the Poisson distribution that the lambda we are using agrees with the questions we are asking, that we have to measure in the same units. So we find here that our lambda is 24 over 52 is 0.4615 per week. And so we can calculate the probability of x greater or equal to 2. Now this is equal to 1 minus the probability of x less or equal to 2. The equal sign, as we said before, for continuous random variables, it doesn't make a difference as in the discrete case. And this here, what we have, we can use the cumulative distribution function. It would be 1 minus the cumulative distribution function we have seen, which, let's do the calculations, see exactly how we derive this. So what we have is 1 minus this, what we are looking. Now we know that here the cumulative distribution function is 1 minus e to the minus lambda x, so we can use it. And we have this. And so this, we see, equals e to the minus lambda x. So we go back to our example. We see we put our lambda, x equals 2, and we calculate the probability of having no breakdowns in a period of 2 weeks, and it is 0.3972. So we have seen how we can use the exponential distribution in association with the Poisson distribution to calculate the probabilities. In this lesson, we see continuous distributions. In particular, we have seen the normal distribution and the exponential one. For more information on this lesson, you can visit the web page of Netuno MedNetU project.